Ever been instantly headshot through a solid brick wall in your favorite shooter and just sat there wondering how on earth that even happened? Well, welcome to this explainer. Today, we're stepping right onto a digital battlefield that honestly, most people don't even know exists. We're talking about a high-stakes, multi-million-dollar cyber war happening right now, completely out of sight, inside your weekend gaming sessions. And you know, this isn't just about someone getting an unfair extra life. This is a rapidly escalating arms race. On one side, you have highly skilled reverse engineers writing cheats, and on the other, security researchers desperately trying to stop them. It's a crazy journey that takes us from the absolute deepest, most privileged parts of your computer's operating system all the way out to custom external hardware and artificial intelligence.
Okay, let's dive right into this. If you play any competitive multiplayer games today, you've probably noticed that modern anti-cheat systems ask for some incredibly deep system access. And frankly, it looks a whole lot like malicious software. In fact, a recent 2024 academic paper pointed out that these anti-cheat systems share the exact same technical characteristics as rootkits. But why? Why are games demanding this level of access to your PC? Well, the simple answer is that an effective anti-cheat actually requires the exact same operating system primitives as a malicious rootkit, just to see what's truly happening on your system. Without that kind of deep power, the anti-cheat is literally just flying blind.
To really understand why this is happening, we have to look at a fundamental flaw in how computers assign trust. Think of your computer as operating on different rings of privilege. Your game, along with older anti-cheat software, runs in what's called user mode, or ring 3. But a cheat can run down in kernel mode, or ring 0, which gives it total, absolute authority over the operating system. And the problem here is that a user mode anti-cheat can be lied to so easily. If it asks the computer to check the game's memory for anything suspicious, a kernel-level cheat can just intercept that request and feed it back completely fake, clean data. The anti-cheat has zero visibility into anything happening at a privilege level above it. So to actually fight kernel cheats, anti-cheats really had no choice but to move down into ring 0 themselves.
This migration down to the kernel essentially created a standard architecture across the whole gaming industry. Now, almost all modern kernel anti-cheats follow this three-component model. First up, you've got the kernel driver sitting down at ring 0, doing all the heavy lifting, intercepting system calls and aggressively scanning your memory. Second, there's a user mode service running with system privileges that handles the network telemetry and actually enforces the bans. And third, you have a DLL injected right into the game itself to check the local state. But here's the catch. Timing is absolutely everything. Systems like BattleEye, for example, they load their driver right when you launch the game. Riot's Vanguard, on the other hand, is way more aggressive. It loads its driver at system boot. Think of Vanguard like a security guard standing at the front door before anyone else even enters the building. Because it's there first, it can inspect every single driver that tries to load after it, making sure no cheat sneaks in during startup.
Now, cheaters obviously know the anti-cheat is watching, so they try to hide their code. They do this by manually mapping it into memory, completely bypassing normal Windows loaders so they simply don't show up in the standard user mode lists. It's like trying to sneak in through a back window. But the anti-cheat writes back with a really clever technique called VAD tree walking. The virtual address descriptor, or VAD, is this deeply internal kernel structure that tracks all the memory regions. Anti-cheats walk this tree directly because, frankly, cheaters can't easily fake it. By scanning the VAD, the anti-cheat can spot injected executable code that has absolutely no legitimate file backing it up. It's basically the ultimate game of digital hide-and-seek, and this is exactly how defenders spot those invisible players hiding in memory.
But man, cheaters are incredibly resourceful. You see, Windows requires all kernel drivers to have a verified digital signature. It's a system known as Driver Signature Enforcement, or DSE. And since a cheat developer obviously can't get an official Microsoft signature for their malware, they use a wild technique called BYOVD, Bring Your Own Vulnerable Driver. The attack chain here is fascinating, and ironically, it completely relies on the very security systems designed to keep your PC safe. What they do is find a perfectly legitimate, officially signed driver from a hardware company like MSI or Asus that just happens to have a known unpatched security vulnerability. They load it up, Windows checks the signature and says, yep, this is an official driver, you're good to go. Then the cheaters immediately exploit that legitimate driver to gain kernel execution, which they then use to secretly map their unsigned cheat driver right into the system memory.
Once that cheat is successfully loaded into memory, the cheater obviously needs to cover their tracks. They want to completely wipe their fingerprints from the system's driver history. So they target these unexported kernel caches, specifically things like the PyDDBC cache table and the M-unloaded drivers lists, and they literally erase their logs. But defenders totally expect this. Modern anti-cheats actively hunt for this exact type of sabotage. They scan the system looking for anomalous zero-filled entries in the circular buffer, or they dig through system memory looking for leftover pool tags that have no corresponding cache entry. If the anti-cheat finds a ghost living in memory with a wiped log, well, that's it. The ban hammer comes down instantly.
So as you can imagine, this endless back and forth in the kernel is just exhausting. And the software protections are getting so incredibly good that successfully loading a software cheat is becoming nearly impossible for your average developer. Which brings us to a massive, game-changing escalation point in our explainer. What happens when the attackers decide to completely bypass the PC's operating system altogether? Enter the PCI DMA attack. DMA stands for Direct Memory Access. Instead of trying to run sneaky cheat software on the actual gaming PC, the cheater plugs a physical, external piece of hardware, specifically an FPGA development board, directly into their computer's PCI slot. Using a specialized framework called PCILeech, a totally separate second computer sitting on the desk can request what are called transaction layer packets to read the gaming PC's physical memory right over a cable. And the craziest part? The gaming PC CPU isn't even involved in this transaction. So, from a purely software perspective, the gaming machine is perfectly 100% clean. There's no injected code, no hidden drivers. Absolutely nothing for the anti-cheat to find.
The technology that actually enables this is absolutely staggering. If you look at the documentation for these PCILeech FPGA designs, it reveals that these tools did not start out in the video game world. Not even close. This direct memory access hardware was originally designed for secure system hosting and real-deal, military-grade forensics. We are literally talking about highly classified technology that was originally applied to atomic and nuclear program security research to audit highly secure systems. And somehow, over time, this incredibly advanced cybersecurity exploitation tool just leaked its way right into the video game cheating space. It's wild.
And the sheer scale and cost of the hardware we are talking about here is just next level. I mean, look at these specs. You've got devices like the ZDMA that are pushing a massive gigabyte per second over a Thunderbolt 3 connection, or the Captain DMA M2 utilizing USB-C. These are not cheap disposable toys. These are highly specialized, expensive, dedicated hardware setups. And honestly, that high cost creates a natural filter. Your casual, weekend cheater isn't dropping hundreds of dollars and spending hours configuring custom firmware just to cheat in a casual match. But for those who do invest the money, these massive transfer speeds allow their external second computer to read the game's memory in real time, feeding absolutely flawless, unlagged data straight to their aimbots and wall hacks.
So you're probably wondering, how on earth does a PC defend against a rogue external piece of hardware literally reading its mind? Well, the primary defense mechanism is something called the IOMMU, the Input-Output Memory Management Unit. This is a physical hardware component sitting on your motherboard that basically acts like a VIP bouncer at a club. It translates DMA addresses, and theoretically, it should completely block any unapproved PCIe device from accessing physical memory it hasn't been explicitly granted access to. It sounds like the perfect bulletproof solution, right? But here is the incredibly frustrating problem. A huge number of popular gaming motherboards actually ship with the IOMMU completely disabled by default in the BIOS. Or even if it is on, it gets severely misconfigured by the operating system, which leaves huge chunks of system memory completely exposed to these DMA attacks.
And it gets worse. Even when the IOMMU is perfectly configured and turned on, the attackers have already figured out a workaround. Cheaters are now taking their external FPGA boards and flashing them to perfectly mimic legitimate trusted PC components. There's literally a Python tool hosted right out in the open on PyPy called PCILeech FW Generator. What it does is take data from real, legitimate donor hardware and generates completely spoofed firmware. So the cheater plugs this FPGA into the motherboard, and the device essentially lies to the computer saying, hey, don't worry about me, I'm just a standard, boring Wi-Fi card. The operating system trusts the fake Wi-Fi card, opens up the VIP rope, and the cheat uses that perfectly trusted pipeline to secretly pull all the game's memory data.
So if you can't trust the software running on the PC, and you clearly can't trust the physical hardware plugged into it, what is left for the defenders? Well, you have to analyze the behavior. Anti-cheats are now fighting back against this invisible hardware by relying heavily on behavioral telemetry. To put that into perspective, let's look at the actual physical limitations of human aiming. When a real human aims a mouse, we naturally follow what's called Fitt's law. We move our mouse in a slight S-curve. We make tiny, subconscious microcorrections, and our hand naturally decelerates as we get closer to the target. A hardware aimbot? It doesn't do any of that. It has an idle phase, and then boom, it executes an instant, mathematically perfect linear snap straight to the target with absolutely zero deceleration. It's physically impossible for a human to do.
To catch those impossible mathematical anomalies, anti-cheat developers are getting incredibly sophisticated. They now capture your raw mouse inputs right at the hardware interrupt level, which gives them insanely precise microsecond timestamps. They then take that encrypted telemetry and feed it directly into massive back-end AI models. And the research being deployed here is staggering. They are using convolutional neural networks to detect the superhuman 0-millisecond reaction times from trigger bots. They're using advanced transformer models, which is actually very similar technology to what powers ChatGPT, to process rolling 256-tick windows of your gameplay. They look at velocity and view angle rates to catch aimbots with over 89% accuracy, and some top-tier systems are even hitting a 99.2% accuracy rate. They're even deploying graph neural networks to track how players interact with each other over time, mapping out social connections to catch wall hacks and team collusion.
But through all of this, the absolutely crucial point is summarized beautifully by this age-old cybersecurity quote: "Defenders must check everything. Attackers need only find one gap." This perfectly illustrates the core, ultimately unsolvable problem of client-side security. At the end of the day, the PC you are playing the game on is physically sitting in the hands of the potential attacker. Because of that massive asymmetry, the future of this arms race is very likely going to have to shift away from kernel drivers entirely. We might see a move toward remote hardware attestation, like using the TPM chip on your motherboard to cryptographically prove that your computer's boot state hasn't been tampered with. Or, taking it even further, we might see competitive play shift entirely to cloud gaming, where your local client simply receives a video feed, making direct memory reading entirely impossible from the start. But, until cloud gaming becomes the absolute standard for competitive play, this brutal battle is going to keep raging right there on your local machine. We are rapidly approaching a point where AI-powered cheats run completely on external hardware, passively analyzing a video feed of the game and using robotic, simulated inputs that perfectly mimic those human S-curves and Fitts law decelerations we talked about. Which really leaves us with a provocative thought to end on. When these AI aimbots operating through completely spoofed hardware become truly indistinguishable from real human players, how will we ever know who is really playing? Thanks so much for joining me on this explainer. I really hope this helps shed some light on the incredible, high-stakes engineering happening behind the scenes of your favorite games. Keep learning, stay curious, and I'll catch you next time.